This little PC has a CPU, a GPU, and another processor built specifically for AI, an NPU. And I know what the CPU is for, and I know what a GPU is for, but I realized I don't really know what I'm supposed to do with the NPU. Is it faster? Is it just more efficient? What kind of AI workloads belongs on this thing instead of a GPU? And I could have just run a bunch of AI benchmarks and compared the numbers, but I don't really think that answers the question. I wanted to find something I might actually run. Something doing AI continuously, in real time, where I could move the exact same workload between a CPU, GPU, and NPU and see what actually changed. But first, what exactly is an NPU, and why would you use this instead of a GPU? NPU stands for Neural Processing Unit. It's basically another processor designed specifically for AI. A CPU is designed to be flexible. It can pretty much run everything on this machine, but that doesn't necessarily make it the most efficient place to run a bunch of neural network operations over and over again. A GPU is much better at doing lots of math in parallel, which is why GPUs have become so important for AI. They're incredibly powerful, and they can run everything from local language models to image generation to computer vision. An NPU is more specialized. Instead of trying to be as flexible as the CPU or as powerful as the GPU, it's designed to run on AI workloads efficiently, especially the kinds of things that might be running continuously in the background. If the GPU can already run the same AI model, why would I move that over to the NPU? To answer that, I needed something more useful than a TOPS number on the box or a synthetic benchmark. I needed a real workload. And video was the first thing that I thought of. Video really never stops, and if you're doing AI object detection, you're running the same kind of inference over and over again, and new frames are constantly coming in, and you want to react to those frames very quickly. Video gives me all of that. It's continuous, latency matters, power matters, and I can see whether the detections are actually useful. And there's already an open source project built around exactly that type of workload. It's Frigate. If you haven't used Frigate before, it's an awesome open source camera security system. It can take feeds from your cameras, record them, detect motion, and with the right hardware, it can also use AI to understand what it's seeing. So instead of just telling you something moved, it can tell you there's a person walking through the yard or a car pulling into the driveway. Frigate supports something called OpenVINO, and OpenVINO is Intel's runtime for AI inference. And in normal human speak, it's a piece of software between the application and the hardware that takes AI models and runs them on the CPU, GPU, or NPU, if that's more human speak. And Frigate already lets me choose which one I want to use for object detection. That gives me a pretty clean way to test. The CPU can run Frigate and the rest of the application, the integrated GPU can handle decoding and video streams, and then I can move the actual AI object detection between the CPU, GPU, and NPU. And I already had a machine sitting around that could do all three. This is the MINISFORUM MS-03, and MINISFORUM sent this over for me to test. MINISFORUM calls this the MS-03 Edge AI Mini Workstation, which is a lot of words for such a small computer, but that's part of the reason why I started asking what the NPU is actually for. This one has the Intel Core Ultra 9 386H, one of Intel's Series 3 or Panther Lake processors. Now this is technically a mobile processor. Intel classifies the 386H as a mobile chip, even though MINISFORUM put this into a desktop workstation. And for this test, the important part isn't really the CPU specs themselves. It's the fact that I have one chip that gives me all three things that we've been talking about. I have a CPU, I have an integrated GPU, and I have a dedicated NPU rated at 50 TOPS. Whatever TOPS means. TOPS stands for trillion operations per second, and in normal human speak, it's basically the measure of how much AI math something can do theoretically every second. For computer vision, more of that compute can mean running an object detection model more times per second. So 50 TOPS sounds impressive, and it definitely looks good on the product page, but I wanted to know what it actually meant on an app I might run. The rest of the MS-03 fits Frigate pretty well too. There's a 10 gig Ethernet card, dual 10 gig SFP+, multiple NVMe slots, and a PCIe expansion. So this could legitimately be a little server running camera workloads and not just a machine I'm just using to produce some benchmark numbers. But there was just one problem. The processor is really new. So on paper, this should have been pretty easy. And around here, we don't do things because they are easy. We do things because we thought they were gonna be easy, and this Frigate container was no exception. Frigate 0.17 already supports Intel NPUs, and I wasn't trying to add NPU support to Frigate. The problem was the Intel software stack bundled inside of Frigate's container. The processor is newer than the stack. That meant rebuilding the container, which is something I hadn't planned on. I probably created a Frankenstein build of Frigate in the process. I mean, it works, and I put the whole thing on GitHub if you want to build it yourself, but I don't expect this to be the long-term way to run Frigate on hardware this new. So I needed to give Frigate something to watch. I could have used my actual security cameras at home, but for obvious reasons, I really didn't want to put my footage around my house all over YouTube. And this gave me a pretty good excuse to actually go outside, for once. So I took my camera around Minneapolis and tried to find a few different scenes that would give Frigate something interesting to detect. I recorded highway traffic, an intersection at a park, people walking and running on a path, and a parking area with cars coming and going. To make the comparison repeatable, I took 4 clips I recorded and turned them into 4 camera streams for Frigate. The way I made those virtual cameras is actually pretty simple. I used FFmpeg to loop each clip in real time, and then fed them into GoToRTC. From there, I published each one as its own RTSP stream. Frigate just sees the camera URLs, even though they're really 4 local streams running in a loop. Once that was running, I kept the same Frigate image and the same 4 camera systems and the same model, which is YOLO V9 Tiny, running at 640 by 640, and the same GPU video decoding settings. YOLO is an object detection model, and YOLO stands for You Only Look Once. It takes a frame and returns the objects it recognizes, where they are in the image, and how confident it is. Depending on the labels the model was trained on, it can include things like people, car, dogs, cats, and lots of other objects. And Frigate uses those detections to track objects across the frame and decide what should become an alert or when to review them. And apparently, this is a cat. It's actually a dog if you didn't know, but the model doesn't always get things right. Better models can detect things better, and Frigate has a version called Frigate Plus where you can actually fine-tune the models that you're using for the cameras. This is where inference speed starts to matter. Every one of those regions has to pass through the model. The faster the detector can process them, the more activity it can keep up with across all of the camera feeds. For each run, I let Frigate settle in, and then I ran the test for about 5 minutes and repeated it 5 times so I wasn't basing it on a single run. Once the test was repeatable, I wanted to capture a few different things. Latency was a big one. Frigate shows the detector's inference speed right on the UI, so I could track what it was reporting as I moved the detector between the different processors. I also captured the detector frame rate. That's my throughput side of the test. Basically, how many detection frames per second is Frigate actually running? But I wasn't only interested in speed. I wanted to see what was happening on the rest of the machine while all the tests were running. I watched power at a couple different levels too. I used a tool called TopsWatch to send power and utilization metrics into Prometheus, and then I graphed those all in Grafana. Now, not every sensor was available, especially the per-device power and GPU thermals. I think that was another side effect of using Panther Lake and it being so new. Then I went through the highly scientific method of plugging the entire MS-03 into a smart plug so I could see what the whole machine was actually pulling from the wall. So for every run, I had inference latency, detector throughput, CPU, GPU, and NPU utilization, hardware power metrics, and wall power for the whole machine. That let me compare the speed without losing sight of the rest of the system. Starting with the CPU, Frigate averaged about 30.4 milliseconds with around 33 detector frames per second across 4 cameras. The whole machine averaged around 51.4 watts from the wall. Then I moved the detection over to the GPU. Frigate averaged about 9.7 milliseconds and throughput climbed to 53.5 detector frames per second. So moving this off the CPU was already a huge step up. The GPU was basically pinned during detection at about 99% utilization, and the whole machine averaged about 24.8 watts from the wall. Then I moved the same workload over to the NPU. Frigate averaged the same 9.7 milliseconds and 53.3 detector frames per second. Now the GPU did 53.5 and the NPU did 53.3, and I'm not going to pretend like 0.2 matters. And Frigate, they're basically tied. The much bigger difference was power. The NPU run averaged about 18.3 watts from the wall, about 6.5 watts less than the GPU, and 33 watts less than the CPU. The NPU itself averaged only about 18% utilization, and because it was doing detection, the GPU dropped back to around 30%, and it was mostly handling video decoding. So instead of asking the GPU to do both jobs, I could just move detection to the NPU and still have most of the GPU available for something else. But that result surprised me a little because the standalone OpenVINO test looked pretty different. And this is where benchmarking gets a little bit frustrating. Before I put the model into Frigate, I also ran the YOLO model through the CPU, GPU, and NPU. For the first controlled test, I used OpenVINO's benchmark app command line tool. I pointed it at the exact same 640 by 640 YOLO V9 model and ran it in latency mode for 30 seconds and changed only the device. The CPU reported 28.6 milliseconds and 34.5 frames per second. The GPU dropped to 4.2 milliseconds and jumped to about 221 frames per second. And the NPU led with 2.2 milliseconds of latency and about 315 frames per second. That doesn't measure exactly how Frigate measures frames, so I tried to set up a more controlled, more Frigate-like synchronous test. That brought the GPU and NPU a little bit closer, but the NPU was still ahead. The CPU averaged about 29.3 milliseconds and 34.2 frames per second. The GPU averaged 5.5 milliseconds and 179 frames per second. And the NPU averaged 4.8 milliseconds and 200.5 frames per second. So both control tests put the NPU in front of the GPU, but that's not what we saw in the live Frigate testing. I'm kind of chalking that up to Frigate's doing a lot. It's also decoding 4 video streams, moving frames around, and processing detections, which could lower the inference number because it's doing some other model work too. When I started this, I really didn't know what I was supposed to use the NPU for. I knew what I could use the CPU for, and I knew what I would use the GPU for. But the NPU was just this extra piece of hardware sitting there with a 50 TOPS number attached to it. I was looking at it more like it was supposed to be a smaller GPU, or something that should win in a benchmark or somehow make AI faster. But that's really not what it's for. It's just another place to put a supported AI workload that you want running in the background all of the time without making the CPU or GPU do it. Frigate is a really good example of that. Object detection is just sitting there and running over and over again all day, every day. And yes, I made an entire video about local AI and I never opened up a chatbot. Now, you can run large language models on the NPU too. Intel supports that through OpenVINO. I just didn't test it here because I wanted to answer a different question. What would I actually use an NPU for? And after all this, I think I have a much better idea. So what about normal people doing normal people things? Well, Frigate isn't the only example. If you're on Zoom or a Teams call on a supported machine, the NPU can handle things like background blur, virtual backgrounds, framing, and other camera effects without leaning so hard on the CPU or GPU. And live transcription is another good one. Speech recognition can run continuously on the NPU while leaving the rest of the system for everything else. And this isn't just an Intel thing either. Apple calls its version the Neural Engine, AMD calls theirs the XDNA, and Google calls theirs a TPU because apparently everybody needed a different name for their AI processor. But the idea is pretty much the same. It's a dedicated piece of hardware for AI workloads that can run without tying up the CPU or GPU. So no, the NPU doesn't replace the GPU, but I finally know what I'd use the NPU for. Well, I hope you enjoyed this video. I'm Tim. Thanks for watching.